Hi, this is Mrs. Villette, and in this video I am going to come up with the rule for differentiating products. But before we come up with this rule, we need some new notation for how we're going to do derivatives. So our normal notation for taking a derivative is to take the limit as h goes to 0, f of x plus h minus f of x all over h, and that represents f prime of x. So I want to unpack what this means a little bit. What we're actually doing is we are constructing a secant line to the function f between 2 points, and we are corresponding those 2 points to x coordinates of x and x plus h. And when we draw that secant line, we are measuring the slope. We're going to measure the rise part of this equation and call it the f of x plus h minus f of x. We're going to define that to be the change in f, or delta f. And we're going to call the run part of this slope the change in x. So another way of writing the derivative would be to say that f prime of x is the limit as delta x goes to 0 of delta f over delta x, recognizing that as I shrink in this distance, the delta x distance down here, to 0, that I am also going to correspondingly shrink this distance, the delta f, down to 0. But we're just going to use this notation delta f over delta x as our slope of our secant line, and then we're taking the delta x to 0. What I also want you to recognize is that from this notation, we can say that my f of x plus h is equivalent to my f of x plus my delta f. So that's the notation we're going to need to come up with the product rule. Okay, so let's go ahead and get started with coming up with the product rule. Our goal is to develop or come up with a shortcut rule for taking the derivative of a product of two functions f and g, and we're going to do that using the limit definition of the derivative. To start, I'm going to define a new function, k of x, to be my f of x times g of x. And what I'm wanting to find is k prime of x. So k prime of x would be the limit as h goes to 0 of k of x, why isn't it erasing? There we go, of k of x plus h minus k of x all over h. But we have to recognize that our k of x is actually a product, so k of x plus h is actually f of x plus h times g of x plus h minus f of x times g of x all over h. Now we're going to change this over to the delta f and delta g notation, remembering that delta f is my f of x plus h minus f of x. Delta g is my g of x plus h minus g of x. And my delta x is basically my h. So we're going to change this to the limit as delta x goes to 0. The bottom is going to be delta x. F of x plus h is actually f of x plus delta f. And g of x plus h is g of x plus delta g minus f of x, g of x. I'm going to go ahead and FOIL out that first factor in the numerator. And so I have f of x, g of x, plus f of x delta g, plus delta f, g of x, plus delta f delta g minus f of x, g of x, all over delta x. The f of x minus g of x cancels, and now we're going to do a little bit of clever algebra and factoring. So looking at this first term in the numerator, I'm going to take an f of x out because f of x has no dependence on delta x, so relative to the limit it's a constant. So I have f of x multiplied by the limit as delta x goes to 0, delta g over delta x. Now in the second term, I'm going to take out a g of x. So I have g of x times the limit as delta x goes to 0, delta f over delta x. And then the last one, I'm going to say limit as delta x goes to 0, delta f over delta x times delta g. If you recognize from the previous page, some of these are actually derivatives. This expression here, limit as delta x goes to 0, delta g over delta x, that's the change in g over the change in x as the change in x goes to 0. That is our expression for g prime of x. Similarly, right here we have delta f over delta x as delta x goes to 0. That is my f prime of x. And I have another copy of my f prime right here. What I have to recognize is this first limit exists. This is f prime of x. But as delta x goes to 0, this expression right here is going to go to 0 as well. So actually I need to have a limit distributed to the second factor, which I can do because both limits exist. I can apply the product rule for limits, not the product rule for derivatives, but the product rule for limits. And we know that as delta x goes to 0, the change in the g function is going to go to 0. So this is actually just a 0. So what am I left with? I'm left with f of x times g prime of x plus f prime of x multiplied by g of x plus a 0. And that is actually our shortcut product rule. If you take the derivative of the product of two functions, so an f of x times a g of x, you keep the first function, differentiate the second, then you add to that the derivative of the first function multiplied by the second. So I'm going to go ahead and add in an example here. Let's say you were asked to take the derivative of the square root of x multiplied by the natural log of x. Now often this multiplication symbol won't even be there and the things will just be written next to each other, so you have to recognize that this is a product. So the product rule says keep the first function and multiply by the derivative of the second. So derivative of natural log of x. I haven't actually taken any derivatives yet. And then take the derivative of the first function and multiply it by the second function. Now we're going to take the derivatives that we can using the shortcut rules. So this would be square root of x multiplied by 1 over x plus the derivative of the square root function. We want to treat this like an x to the 1/2. So it would be 1/2 x to the negative 1/2 multiplied by the natural log of x. We need to do a little bit of algebra. So the first bit of algebra I want to do is to combine these like bases. This, again, is x to the 1/2. And so if I subtract in the denominator, so x to the first minus 1/2, I will get 1 over the square root of x. This second factor has a 2, and then I'm going to take that negative exponent down into the denominator as a square root. Since my original function was a product, I want to try to write this as a product if possible. And in fact, we might want to go ahead and write it with a common denominator. Multiply this one by 2 over 2. So I get 2 plus the natural log of x over 2 square root of x. Now you'll notice that's not really a product, it's a quotient. So if I really wanted to write it as a product, I would say 1 over 2 root of x multiplied by 2 plus natural log of x. Or we could have not done the common denominator and just factored out the 1 over root x and did 1 plus natural log of x over 2. I like this first way a little bit better, just because it's a little cleaner. It doesn't have as many fractions in it. I would go ahead and compare that to what you get in Wolfram Alpha, so let's take a look. So you can see how I entered this into Wolfram Alpha, DIFF, and then I did SQRTX, that's the square root of x, times, which is asterisk, natural log of x, comma x. Now one thing to know about Wolfram Alpha is it changes the natural log into what we would think would be the common log. They say that somewhere that that's what they're doing, but this should be interpreted not as common log, but as the natural logarithm. So the answer they gave was log of x plus 2 over 2 root of x, which is most similar to this answer. The only difference is that they wrote their logarithm first and their constant term second. There's some pretty sophisticated algorithms within Wolfram Alpha to decide how to rewrite the answer, and most of the time it is that idea of matching it to the original form, but there will be cases where you'll see it slightly different. But I'm pretty happy that this is the result that we got and this is the result that they got. Okay, so that is the end of the video. Hopefully you have an understanding of where the product rule comes from. You are expected to take notes into your notes, and I will check them when I return, and to also work on the different things that are listed on the subplan, like the free response question and finishing the product rule worksheet.